Yes, hi everybody. Yes, my name is Brandon Cugini, and today I will be talking to you about my thesis project that I did for my undergraduate degree, where I used LiDAR images of a segment of a fault, the Lavic Lake Fault, in the Mojave Desert to interpret the slip characteristics of the 1999 hectomine earthquake, which is 7.1 magnitude. And so the rationale for this study is that LiDAR is a relatively new type of analysis we can deploy on service locations to determine what's going on. And it's actually employed at a lot of different earthquakes, but also it's been used for many decades in the world of volcanology because what it can do is it can detect subtle changes in things like dome characteristics. So you can determine whether or not lava is rising to the surface. But in this case, we are looking at a strand of fault, and as you can take a look on the actual right, the Lavic Lake Fault is a strand of fault that actually was activated during the 1991 hectomine earthquake. And it's actually located in a very seismically active part of the state called the Eastern California Shear Zone, which is basically a set of right lateral strikes of faults that move right to relative where you're standing, uh, that run parallel to the San Andreas Fault around the Mojave Desert. And the reason why this is important is because it's seemingly every 10 years we have a major earthquake that happens along this fault line. Most recently, we had the Ridgecrest earthquake that was 7.1 in magnitude. But the rationality is that in the year 2000, there was a set of LiDAR images that were produced and were analyzed by a man by the name of Chen Tao in 2015. And in 2012, there was another set of LiDAR images that were never analyzed. They were basically shelved and nobody took a look at them. So therefore, what I aimed to do with the study is that I wanted to replicate the results that were found in 2000 with 2012 data with the hope of being able to have some historical data with the offset to determine how these tributaries that have been truncated that we're looking at change over a 12-year period. In addition, we're comparing this to fieldwork that was conducted in 2014. And so the methodology basically goes like this. A man by the name of Bob Wallace, 1968, realized that when an earthquake happens, it can truncate features that intersect it. So as you take a look over here, we have a stream channel that's been truncated along the San Andreas Fault. And you can measure that to get an inference as to how much the earthquake moved, or which actually goes into calculating magnitude of the earthquake. And this is a good way to get ancestral earthquake data from surface features. And so basically what happens is that as a feature gets truncated by the fault, like this fence, it moves, and you can measure that to determine the slip distribution, the slip magnitude. And so what we're doing here is instead of going out in the field and taking our own direct measurements, I'm using a proxy through LiDAR. And basically what happens is that digital elevation models, which are basically raster images where you have different pixels that mean different elevations, are taken by the use of LiDAR. And basically what happens is that we have an airplane that runs over the actual fault strand that sends out beams of light, and is a machine that takes into account the time it takes for the light to bounce off the surface and back to the machine, which actually have many thousands of these different light beams that are taken to track of. So as a result, we get very high resolution images that are produced in these digital elevation models. And these digital elevation models preserve information, including elevation. So what I do is that I mark where the fault is. So basically what I do is that I take these images of them, I crop them down to a specific feature that I want to look at. I outline the fault, which tells the